Usually I talk about, I've been in this conference a couple of times in the past, about very analytical results. Today I'm going to show something somewhat different, along the lines of some of the discussion that Ido Kaminer, who's collaborated with me on some of this work, discussed, using basically algorithms in order to try and identify new potential formulas in fundamental physics. Before I actually start, let me just say I had a very long night with a 1-year-old that refused to let me sleep, so I'll try to do my best to keep this as coherent as possible. I'm going to start by saying a few words about AI, which is part of the reason we started this work, and then describe two different works. The first one is a work that was already published, that is called the Ramanujan machine, which is basically an algorithmic approach in order to identify new formulas in number theory. And I'll mention this. And the second is about the Planck machine, which is more preliminary work about finding formulas in fundamental physics, hopefully. So a few words about the AI revolution, and very, very briefly. In the last few years, multiple really interesting events happened in the world of computer science as it related to artificial intelligence. Okay, the first one, we've seen computers beating humans in a lot of different games, okay, in a lot of arcades, but also things that are much more complicated. The most famous one is AlphaGo, that won in Go against the world champion. We also have seen AI beating humans in image classification. There's been a competition for more than a decade about image classification. And since about 2015, computers beat PhD students actually in image classification. And computers got so good at it that about 2-3 years ago they stopped having the competition the way they typically do it and changed the competition to make it much harder for the computers. In the last competition that they had with this, in this way, 2020, all the groups beat all the PhD students, basically. Every algorithm beat all the PhD students that were tested on it. Now, this is of course outside of the realm of like, let's say, direct science. So you can also talk about AI and the way it's affecting science. So in 2019, a group from UT Austin actually used artificial intelligence in order to discover 2 exoplanets from observations that were overlooked by actual scientists that were looking at the same data. And more recently, there is a famous case of DeepMind AlphaFold that actually predicted protein structure very successfully. Now, last comment about AI, and then I actually get to my actual talk. You can actually ask AI researchers about, when will computers beat humans in certain other activities? Igor, this is related to your comment to me earlier. Researchers from Berkeley and Oxford did this research, and you can see the predictions. I'm very happy to tell you that things like math research and physics research are at least 40-50 years away, according to the median that was asked by the scientists. Now, the question I want to pose today is slightly differently. I'm not looking at AI in the sense of, how it can replace the kind of things that we're doing, but actually how can it help extend the kind of things that we're doing? How can it guide research? My advisor, Vladimir Zakharov, used to say science is infinite. It's never going to end. There will always be interesting questions to ask. Now the question is, if it is infinite and if there are so many questions, can AI or can algorithms actually help us find questions that are more interesting to ask or are more likely to work? And this is the question that I'm going to pose in this talk. And I'm going to start with an inspiration from the world of mathematics. So in mathematics, everybody hopefully know Ramanujan, who discovered these beautiful, beautiful formulas like the one that you see that is relating pi and e to a lot of natural numbers. Ramanujan was very famous for discovering a lot of formulas without providing formal proofs. Now, while doing that, he actually set challenges to generations of mathematicians that took years, sometimes decades, to actually prove a lot of his conjectures. As a result of that, he also ended up opening new directions of research. And as an inspiration, the first goal that I want to set here is really, can we build a computer program that potentially helps us find new conjectures in mathematics that relates mathematical constants? Okay, so I'm going to show you in a moment that the answer to this question is yes. And what we're going to do is basically look at formulas that are similar to the continued fraction that you see here inside the red rectangle. This work that is a result of work that I've done together with Ido Kaminer, who spoke here earlier, and his students, and was published in Nature about 2 years ago. And we basically started by taking formulas where on the left-hand side you have a continued fraction of a famous mathematical constant, okay, pi, e, and others that I'll show in a moment. And on the right-hand side you have continued fractions, but with some patterns, okay, with some patterns in their numerators and denominators. Okay, usually polynomial patterns, but sometimes things that are more complicated. Now, if you had an algorithm that could analyze such formulas, for example, you can try and plug in, I know it's really small and hard to see, hundreds of the famous constants in mathematics and see what happens. And we've done this. Because of time, I won't describe the actual algorithms. We developed multiple algorithms that do this. I want to jump into the physics result earlier. This is called the Ramanujan machine, inspired by Ramanujan. And you can see here on the left some of the formulas that were found by one of our algorithms. Those specific ones were novel conjectures that have very short proofs that we were able to prove, or the community was able to prove. And you can see, if I find out how to use this laser, here we go. You have like pi on the left side here, and you can see here this is a linear formula, a linear relation, all the natural numbers. You can see these formulas have really beautiful patterns, right? E and all the natural numbers, and again, okay? Now this is one example. Another example that is more complicated, once we start extending beyond just polynomials, those are formulas that were conjectured by the computers, but very importantly, except for two of them, that changed obviously since the paper, we actually don't know of proofs to some of these formulas. Okay, so there are a lot of other novel conjectures that the computer derived that were validated up to over 1,000 different digits. That seem to be true and can be new directions of research in number theory.
May I interrupt? Those two formulas are related to the zeta function?
Yes, so both of these.
Which can be proven, yeah?
The second one and the third one are the zeta function. Yeah, correct. Yeah. G is the Catalan constant. Catalan constant from number theory.
Can't hear you.
Keep going. I'll keep going, so because I have. Okay.
Ignore all the questions.
Sounds good. Sorry for ignoring everybody. Just a few other takes before we go into physics. So we discovered thousands of conjectures. Some were known, some were unknown. There are over 100 different conjectures that are novel and still are proven up to this point. We got a world record on convergence rates of certain formulas, specifically the Catalan constant that I mentioned before. We proved multiple new theorems related to number theory. Some of them are not yet published. And this is probably my two favorite, are the last ones. We were able to create a very engaged community, over 10,000 members. Some of them are experts, some of them are amateurs that are really into mathematics, that are looking at the formulas and trying to prove them. And by far my favorite, because for me a big goal here was to actually inspire people. We had one very young person, a 15-year-old girl, who was able to prove a novel conjecture and has now a theorem under her name. Okay, so now this is great. This is mathematics. I presented this part more because this is like published work, more established first, so you take me a little bit more seriously. And I'm going to show more preliminary results related to physics. How am I doing on time?
Basically 10 minutes altogether, 8 minutes altogether.
Okay, thank you. And I'm going to ask the same question. Could we study now physical formulas with similar approaches, but formulas that are related to physical constants? Now once you start to think about this is a very different question, right? It seems very similar, but it's actually fundamentally different for two reasons. First, physical constants have dimensions, okay, so they cannot just be equal to pi randomly, so you need to take that into account. And second thing, unlike all the formulas I showed you before, that we can run algorithms that will test as many digits as we want, right? It's mostly dependent on computational power. Physical formulas always have bounds on how well we know them. We know them up to certain digits. We don't know them ad infinitum. And we cannot even calculate them ad infinitum. And as a little bit of an inspiration, this is like what we kept in mind when we were thinking about it. Think about this formula for the fine structure constant, okay? The fine structure constant, alpha, is dimensionless, and we know that it's related to both E, the electric charge, okay, electromagnetism, permittivity of free space, H bar, which is related to quantum mechanics, and C, the speed of light. This is a dimensionless constant. Imagine that one day, we all of a sudden have this beautiful formula that relates this to different mathematical constants.
You just saw it.
What?
You just saw it.
Oh, I mean of a way to calculate alpha independently of these constants. Okay? That, even if we didn't know the theory that leads to it, that would be a hint that will help us try to focus our attention on things that are more potentially relevant. Okay, so another historical example. I love this one because when I found this I was shocked. Here I'm showing you a whole paper. This is the shortest paper I've ever seen in physics. It's 3 lines. It was published in 1950. And that paper shows a really interesting result. If you take the mass of the proton divided by the mass of the electron, it ends up being equal to 6 pi to the power of 5. However, since this paper was published, experiments shown that it's only an approximation and it's not accurate. Now, let's ask ourselves, are there going to be more, hopefully exact this time, relationships that we don't know about? And I'm going to tell you that the answer is yes. In a second, I'll show some very preliminary results on this, okay? So the premise related to the Planck machine, and maybe a word about why it's named after Max Planck. So Max Planck is probably most famous contribution is black body radiation and the Planck constant. That was as a result of analyzing experimental data and extracting a constant out of it. So we got his cool name attached to this work. And here's the premise. We're going to start on studying equations where on the left-hand side you have dimensionless physical constants to some powers. Those powers can be positive or negative. And we're going to try and find mathematical constants for which they're equal to in that form. Okay? Now, important comment here, a lot of formulas that you know already fit this criteria. The Compton formula, you can put all the constants on the left, here you have the one on the right. Bohr's formula, you can put all the constants on the right and the 2 on the left, and the 2 is the C here. So a lot of known formulas could be put in this form. And what I like about it is that you can take the log of it. Okay, this is a simple case relatively, and you get a linear equation. What we're going to try and find are formulas that obviously we cannot. Okay, this is physics now, right? We cannot have it equal exactly because we don't know the error, the potential error. But what we're going to try and find are integer solutions where these alphas, betas, and C are going to be integers, and they're going to be bound by the measurement of the experiments related to this physical constants. And this is how we do it. Fortunately, when we're trying to do this, there are known algorithms for solving integer relationships. One of them is PSLQ. I won't describe it in too many details, but I want to describe the methodology and then show you examples and finish here of the things that the computer discovered. So here's what we're going to do. We're going to take a database of physics constants. In the case that I'm going to show you right now, I ran my computer for 24 hours. It's an old MacBook, maybe 4 years old. And I ran it over 36 physical constants that you know. C, H bar, mass of the electron, charge of the electron, etc. They have dimensions. We need to get rid of the dimensions. There is a famous formula in applied mathematics, a famous theorem, Buckingham pi theorem, that lets you get rid of the dimensions. And when you do that, in this case, you're left with 31 dimensionless physical constants. For example, the mass of the proton over the mass of the electron, different than 6 times pi to the 5th, right? In addition, we're also going to input which mathematical constants we want the computer to look over. In this case, I took 5 constants, pi and a few others that you'll see in a moment. And what the computer is going to do is pick every possible combination of physical formulas, any possible combination of mathematical formulas, enumerate over all of them, and use that algorithm that I mentioned before in order to find formulas that use those combinations that fit the experimental data. If they don't, we throw them away. Okay? When you do this, you're going to get a lot of candidate formulas. Guess what? It's going to be, excuse my language, shit tons of formulas, over 1 million formulas. Okay? Now we need to start getting rid of them. Now the challenge is that a lot of the formulas that you're getting are actually known formulas or derivation of known formulas. So one of the things that we added to this algorithm is a method to take a database of known equations that we took from Wikipedia and a lot of other sources, and use them in order to eliminate whatever is derivable from known results. If it's derivable from a known results, it's great. It shows that the algorithm finds stuff that makes sense, but it's not going to help us discover anything new, right? So we sort of trash it. We put it aside, and I'm going to show you that the algorithm actually discovered it. So you see that it at least works with a lot of known results. And if it's not derivable, we save it as a new candidate equation. Now, the problem is there are still at this stage many formulas, okay? So we are trying to find other ways of extracting what could be more interesting or less interesting. I invite you after my talk, if you want, or in the break, to come and see the PDF the computer generates, like 1,000 pages of formulas with, that are difficult to distill. So what we did are two different things. First of all, we calculate something called an uncertainty score. The uncertainty score is basically the, if you want, the log of the combined uncertainty of all the constants in the formula. So basically, if you take something like this equation, you put all the physical constants on the left, that's going to be the number of digits that we know are correct for that specific formula. Okay? Why do we care about it? Because the more digits we know accurately, the less likely it is to be a numerical fluke. Okay? Secondly, we're also going to look at something kind of like invented, which is a beauty score. How simple a formula is. Okay? This is like a hope to find a beautiful potential formulas. In this case, what I did with a beauty score is very simple. I just add up the absolute values of all the powers of all the constants that you get in the equation. So in this case, you have power of 1, power of 1, 1 and 1. The beauty score of this formula is going to be a 4. Okay? More complex the formulas there are, the beauty score is going to be higher. I guess you should call it like ugliness score, maybe. And then you get a database of ranked candidates. Now many of these candidates are going to be results of other candidates, right? So what we're going to do, we're going to use the uncertainty score and the beauty score to eliminate out of those 10,000 formulas anything that can be derived from other ones, and we are going to be left with a basis of formulas that are simple within like reasonable uncertainty score and can derive everything else. Okay? And I'm going to show you a taste of the examples. This is not yet published. We're going to post it on archive over the next few days. So for example, this is what we get after a 24-hour run of this formula. The G's here are the G factors for different particles: proton, muon, and neutron. And you see pi here and the cubic root of 80 for some reason. There are other formulas relating ratios of different particles, of masses of different particles, and so on. Now, one of the things that you may ask yourself, what are the beauty scores, uncertainty scores of these formulas? I'm going to show them, just a few of them, right here. So these are things that the computer already discovered. You can see known results: Compton, Bohr, Rydberg formula, and the nuclear magneton. All of those have uncertainty scores of -9, meaning that we know them up to 9 digits, and a beauty score of 4. Our best formula so far, I only ran it for 24 hours, is basically it's this one, the one on the top left, that has uncertainty score of -7, so we know 7 digits of it accurately. It is within the experimental data, that's very important. And also a beauty score of 4, and there are the other results. Okay.
No E, natural logarithm E was not used?
I think that I ran this a while ago. I think that when I ran this, it was without E. So I can try to run it again with E.
How the beauty score is defined?
The beauty score is the sum of the absolute values of the powers of all the constants. So here you have a 4 plus 1 plus 1 plus 2 plus 4 plus 1. That's subjective, obviously. One last slide and I'll be done here. Some obvious next steps. This is very preliminary work, obviously, the second part, the Planck machine. One of the things I would love to do is to try and calculate the probability of any one of these formulas to be a numerical fluke. We already started doing some work on it. And I would love to extend that work to more complex cases to see if we can find other formulas. I would love to go hunt alpha and see if we can find anything interesting there. But I have to say, you can generalize this for a lot of, the general gist of it, to a lot of other directions. You don't mention one related to quantum gravity. You can try to use it to suggest analytic solutions to ODs or PDs, specifically for physical applications. You can try to take experimental data and use algorithms to try and find symmetries in that experimental data. I think that would be a super cool project to do. Or even suggest Lagrangians over experimental data. And those kind of things can have unbelievable implications for other fields, unlike physics, that don't have as much theory or mathematical theory like biology, for which the data is a complete mess, lots of noise. It will be very difficult to find formulas, and here's a great tool, or types of tools that we could use for that. I'm going to end there. Thank you very much.
Well, may I ask, you at the back, sir, with the lighter shirt, because you haven't asked a question in my experience. So we have time for only one question. I'm sorry, Professor Stevens.
Oh, thank you. Very nice and interesting. Can you please elaborate more about which AI model you use for both?
Yeah, so in the third...
Vision and Planck?
Yeah, definitely. So I wanted to mention the topic of AI because I think it's related to the theme. But you know, when people talk about AI, things are always... sometimes people don't agree about what exactly is the definition of AI. In the case of Planck machine, there isn't anything that you could call per se AI algorithm today. Okay, the PCLQ algorithm is an integer relationship algorithm, right? In the case of the Ramanujan machine, we did a couple of algorithms that are based more on numerical methods, somewhat similar more to what I showed with Planck machine, and there was one that was using very heavily gradient descent, but not specifically neural networks like people typically use. So there are ideas from the world of AI, but maybe not per se like what people would call AI algorithms. Yeah.
Thank you. I'm sorry that we have to truncate this now. Thank you very much.